letter to his daughter, a famous quote of his, which is, "It's the most beautiful water he'd ever seen." And it still is. It's quite a beautiful lake. But that quote is where we get the name the Jefferson Project at Lake George. And really what it is in our next slide, the partnership that developed, inspired by those human impacts between IBM Research, the Fund for Lake George, and Rensselaer, taking all of the strengths of all of our partners and having this mission to take a very advanced technological approach to understand what's happening, what are the natural and human impacts on Lake George, and to come up with solutions, figure out how those solutions successful, and to not stop at Lake George. Use this as the sort of the test bed for advanced lake research, and as you'll see later, taking this other places now that we've really got some really mature technology and some understanding about some really important human impacts. And we're on slide 6 now. These are goals. It really was to create what we call the smartest lake in the world. What does that mean? That means to have the most advanced sensors, the most intelligent sensors, the highest resolution computer models to understand how lakes behave and why they behave the way they do. You need that understanding if you're going to mitigate human impacts and problems with water quality, et cetera. So we wanted to be able to export those technologies to other lakes, and we'll talk about that. We want to have this long-lasting intellectual expertise, infrastructure on Lake George, and you'll see how that becomes incredibly important just in the past month. So we'll talk about that. So in our next slide, this is the approach that we take. We monitor the lake in advanced ways and traditional ways to understand how it's behaving. We do experiments to tease apart the reasons why it's behaving the way it is, and we use modeling to predict what's going to happen in the future, whether it's incorporating climate change or incorporating different human impacts and different strategies to fix lakes like Lake George. In slide 8, this is just the overview of what we're going to talk about, and I promised I won't talk for more than 25 minutes so that you have time for some questions, and we just hit the highlights of what we're doing. So there's the roadmap of tonight's talk. And we'll get to it. There's traditional monitoring, and we'll go right to slide 10. Traditional monitoring is the kind of monitoring for things that advanced sensors don't yet do very well. So, for example, in all those black dots that you see in front of you on the maps of Lake George, those are places where we go out and take water samples, bring them back to the lab to figure out where are the hot spots of nitrogen, where are the places that nitrogen is coming into the lake, and that gives us an idea of where we might have human impacts leaking nitrogen, whether it's water treatment plants or failing septic systems, or whatever it is. And you can see in the red a few places around Bolton Landing and around Lake George Village, et cetera, that pop up from time to time. We can also see, if we just look at, in the next slide, the amount of algae growing. We call it periphyton. That's the algae that makes a dock or a rock slippery. We go out and we measure that all over the lake, and you can see the hot spots of where algae grows. And where algae grows is where nutrients are coming in. A lot of those places are the same places that we see phosphorus and nitrogen coming in. And that helps identify where folks might want to put their efforts into upgrading septics or upgrading wastewater treatment plants or stormwater runoff. You see some of the places around Bolton Landing, Ticonderoga, et cetera, on the north end. So all of this is kind of the traditional sampling that we do. We also sample the food web. We don't have sensors to examine the food web. And the food web is everything from the little invertebrates, the clams, the mussels, et cetera, all the way up to the fish. And it's complicated, as you see in slide 13. This is just one portion of Lake George food web. The lines indicate who eats whom. It's not only physically and chemically complex in lakes, it is biologically complex. This is maybe a fourth of the species that live in the lake. So you can see the challenge is immense to try to figure out a lake like Lake George, not to mention, it's about 30 miles long and about 200 feet deep in the deepest spot. So it's a challenge to figure out what human impacts might be doing. Let's move on to experimenting, and in slide 15, you'll see one of our new facilities. This is out at the RPI's Technology Park, which is a few miles from campus, where when I came here in 2014, we built a new experimental facility. And what you're looking at really are mini Lake Georges. These are 300-gallon containers where we can independently manipulate just about anything, whether it's global warming, pesticides, microplastics, anything you want. These all contain Lake George water. We truck it down from Lake George. We get permits to do all of this, and we fill these tanks and can manipulate all sorts of different things because we want to understand how each one affects water quality alone and in all kinds of combinations. So we do a lot of that work as well. So this is under pretty controlled but semi-natural conditions. In the next slide, you'll see we can do this under really natural conditions. We call these in-lake mesocosms. And what you're looking at here is Lake George, a dock system where we have floating plastic bags. They're about 4 feet in diameter, 10 feet deep, under really good sort of natural lake conditions. We can ask, what happens if you change the conditions in each one of these bags? What happens if you add nutrients? What happens if you add road salt? We're always very careful. We don't add anything that isn't in the lake already that would do any harm to the lake. But we can do very, very natural experiments to try to understand what's happening in the lake. So let's then go on to high frequency monitoring. And in slide 18, you'll see where we start that. And that's with a very high resolution map of the bottom of Lake George. So everything in gray and green is above water. Everything in red, yellow, and light green is below water. And the first thing you notice is Lake George has tremendous three-dimensional relief on the bottom. And that causes all kinds of interesting features, different habitats, different ways that the lake has to circulate around these hidden islands and these emerging islands. The highest resolution map of any lake in the world, and that becomes really important when we want to start modeling how things move around this lake. So we have this high resolution map. It's about I think it's about half-meter resolution, so incredibly detailed map of the bottom. And with that map, we can also tell us, where you see rock bottom, where you see clay, where you see silty sediments, which becomes important for things like understanding the niches of different animals and plants and where they live. So we layer on top of that the smart sensor network. And then what that is a network of different kinds of stations. So we have weather stations that measure the kind of things you would expect. Tributary stations that are measuring what's coming down the streams into the lake. So you want to know things like how many nutrients are coming, how salty is the water, etc. You have what we call ADCPs. These are acoustic Doppler current profilers, and what they measure is how the water is flowing from the surface down to the bottom, whether it's flowing east, west, north, south. And the reason you want to know that, as you'll see in a few slides, is the surface water can be going in a completely different direction than the deeper water. And that's just because the wind is pushing the surface, etc. So you get some really interesting measurements of water flow, and these can measure water flow every meter as you go down through the water, down, say, 55, 60 meters, and can measure that in bins, kind of like a radar gun measures car speeds. This is signals that bounce off particles and tell us how fast and what direction the water is moving. So that becomes really important, as you'll see. And finally, vertical profilers. They get their name because they are taking a profile of the water column from the surface down to the bottom, measuring along the way what's the temperature, what's the pH, what's the oxygen, how much chlorophyll, that is how much algae do we see. And we have those scattered about the lake in strategic areas as well. All of these are connected together as one sort of networked sensor in a really intelligent way. And you'll see in the next slide what we've done, and this is particularly where one of their IBM strengths comes into the collaboration, building these single board computers. And we can add these to sensors that we build or sensors that we buy commercially and insert these sensors. They have a Raspberry Pi as their intelligence. As we'll talk about, they can add so much capability that commercially purchased sensors were never intended to have, and we can really get much more out of them by doing that. And we're up to slide 21, it looks like now. Let me check. Yes, 21. We're really excited to be building some of these sensor platforms, like the one you see here, this vertical profile. We build them at RPI. We got kind of frustrated that commercial sensors didn't do everything that we wanted to do. So we work with the engineers at RPI in the CATS group, which is now known as the MIC group, and IBM engineers to develop sort of the ideal sensor. Again, in that white housing that you see, we have a set of probes, which is the lower left picture, And those probes go down on a computer-controlled winch to the different depths and measure the conditions. We have better solar power. We have better bandwidth. On top of it, we have a weather station attached under the water. We also have these current profilers to measure the currents. It is a really high-tech, more advanced than you can buy commercially, built right here at RPO. We now built 3 of them, and we're hoping to build even more of them. They're just incredibly useful and capabilities, so we can add on additional sensors. And we designed this from the beginning so that we can continue to expand the kind of technology that we can add on to that. In the next slide, you see a map of Lake George, and what this is really just telling you is we have this lake covered in sensors, some at the surface, some at the bottom of the lake, measuring things on the streams, more than 52 major platforms with 500 sensors. And I mentioned this is a sensor network, and it's really important because a sensor network, an interconnected bunch of sensors, allows you to do some really intelligent things that each sensor by itself doesn't do. And we can add intelligence, these IoTs, Internet of Things kind of monitoring. We can make the sensors do really what we call adaptive sampling, which means, for example, if you know that there's a rainstorm or a snowmelt event coming, we can feed that information to the stream stations, and the stream stations can make intelligent decisions about when to sample, how often to sample, how to use their power in the most optimal way, how to use their bandwidth in the most optimal way. And we call all of that adaptive sampling. That is, if you could stand there 24/7, 365, it's what you would have the sensor measure. But now we add intelligence so the sensors can do that for us. We can have sensors talk to each other, compare notes, so to speak, in terms of what you're seeing. Am I seeing an outlying value? Are the sensors around me also seeing an outlier value? Maybe there's a pollution event. Maybe there's a leaking wastewater treatment plant. That's the kind of intelligence that we can bring by having not just a collection of sensors, but a collection of sensors that talk to each other. We also have edge computing that allows us to do some of the QA/QC work at the level of the sensor, to tip us off if any outlying values are coming in, et cetera, if the sensors are drifting. All of that is part of the intelligence that we have. So we go to the next slide, you'll see that we also are working on nutrient sensors, not only testing out commercial ones, but working with Dublin City University with a new generation of phosphorus sensors, and then working with Shayla Sawyer's lab at RPI, who's developing a living sensor based on bacteria. And that's going very well to think about how bacteria might be really sensitive to phosphorus levels, and have these bacteria, which have little nanowires connecting each other, talk to each other and give us a signal whether there's a low, medium, or high amount of phosphorus in the water. So that's in progress right now, and we're really excited. It's going quite well in terms of having new generations of nutrient sensors. The next thing we move on to is computer modeling. And in computer modeling, and we're up to, I think, 26 now, this is just an overview of the kind of computer models that we have. We have weather models, the highest resolution weather model in the world. And we want that because Lake George is surrounded by mountains. So, at one end of the lake can be very different weather than the other end. So very high resolution weather model. We're about, typical is maybe 5 kilometers or so grid. We're at 0.3 kilometers, and we're trying to move that down to 111 meters. Great resolution on weather. A runoff model to tell us how the water is going to come in during rain events from those streams. The circulation model that we talked about, which is measuring how water circulates and then using the model to predict it, and that's going to be important in a moment. And then a food web model, bringing the biology into all of this. So these are coupled operational models. What does that mean? Coupled means they are talking to each other. So the weather model feeds information to the other models. The runoff model feeds information to the other models. Operational means they run every day. So each day we have predictions. What's the weather going to do? What's the runoff going to do? What's the circulation going to do? And ultimately, how's the food web going to respond? Never been done before in the world. The Jefferson Project is working on those things right now. Let's jump to the next one. Here's just a snapshot of one of our weather models and circulation models and runoff models together. There's a lot to look at here, but basically the lake is in the middle of this picture. And the streams are those sort of lines of bubbles. And all this really is trying to communicate to you is we can have our researchers look at what the weather's doing, what the runoff is doing, what the lake is, how the lake is circulating, and all the parameters we measure. We can have models predict all of this, and those little crosshairs, the researchers can move around the lake and get predictions of what's going to happen. And we find that really useful to visualize all of this. It's complicated, but you can visualize all of this at the same time. So again, really advanced coupled operational models. One of the very helpful parts of our circulation model is that we can track particles as they might move. Here we're looking at 3 days in June. On the left, a windy day, in the middle, a calmer day, and on the right, another windy day. And I've just sort of done a freeze frame here, and you can see if you were to drop something, let's say a pollutant, down at Lake George Village on the south end at the bottom of your screen, how would that move? Where would it move, and how deep would it move? In purple are deeper waters, and yellow is surface water. We can predict how things are going to move, and we can run that in reverse to tell you if you find, say, some signal of a spill of something, we can run it in reverse and ask where did it probably come from. So these are really useful models for people working in policy, people making decisions, or say the New York DEC wanting to understand how a spill of something might have happened. And we'll get to that as well in a real world example of how that's useful. Going to 28, simple overview of the food web model, and what we're trying to do here is what people typically do in lakes is they just use a one-dimensional model, which is just asking what happens in the middle of a lake and forgetting about most of the biodiversity. What we're trying to do is ask what happens in the middle, what happens at the bottom, and what happens along the shoreline, because the shoreline community, the species that live in the shoreline are most species in any lake. So we're trying to really understand that complexity. Certain species only live in certain places. So we have that as a challenge, and we're making very good progress on having those coupled food web models as well. And finally, why do we do all this modeling? It helps us build what we call a scenario engine, and that's on 29. The scenario engine is a way to work with policymakers to say, give us a scenario where you want to mitigate a human impact. Give us a scenario such as you'd like to cut road salt pollution by half. You'd like to cut nutrients by a fourth. What's the likely impact? How big of an impact? And how long will it take to see those? And you can overlay global change. You can overlay all sorts of things going out decades. That's something that the project is working on, and we know from decision makers, they find this incredibly practical and useful, and we continue to work on that. This is based on all of those previous physical and biological models. So we've got to get all of those models working well, and then we can use those, validate those to predict what's going to happen. Validation is such an important piece. An awful lot of folks make models that are not validated by real data. All of ours are validated, and that's a key differentiator between what we do and what some other folks do. I encourage you, if you have a chance, here's the website, jeffersonproject.live. You can see real data coming in right now from our various sensors. You can look at the high-resolution weather forecasts. You can look at the long-term trends, 40 years of data, and what's happening to Lake George. You see an example of salt in your lower right. We want to be as transparent as we can to the public, share data with them, show them what's happening in the lake, show them what's happening in the last 40 years of the lake. Don't believe us, see it for yourself, and we find that to be really great outreach. And this went live about 5 months ago, and great feedback from the public in seeing the kind of data that we're bringing in. In our next slide, we want to talk about expanding the JP to other water bodies. This has been the plan since day one, that we want to move the Jefferson Project, once it matures in the technology on Lake George, go and take it to other places and help other communities solve their water problems. As you may know, this is probably the biggest issue. In the next slide, harmful algal blooms. It is a regional challenge. New York and New Jersey are really the epicenter of harmful algal blooms if you look across the country. It's happening across the world, but the Northeast, particularly New York, New Jersey area, it is unbelievable how many harmful algal blooms that we're having. In late 2017, the Governor Cuomo, created his Harmful Algal Blooms initiative and picked 12 lakes. Lake George is one of those 12. And Lake George is one of those 12 because of the 12, it was the highest quality. It had never in its history had a harmful algal bloom, as far as we know. Other lakes on that list of 12 are really bad in terms of having real problems with harmful algal blooms. So we're fortunate because, as you see on the right-hand screen, in red and orange are confirmed harmful algal blooms, and harmful algal blooms make toxins, which is coded in red. So we care about harmful algal blooms primarily because harmful algal blooms are largely this group of algae we call cyanobacteria. Cyanobacteria, some of them make some very nasty chemicals and release them into the water. There are nerve toxins. There are liver toxins, there are skin irritants. When pets go in and groom themselves afterwards, they sometimes die. It's a real human health issue, not just a sort of an ecological and water quality issue. It's a major drinking water issue. You know, for example, about 2014, Toledo had to shut off their water intakes from Lake Erie because of a harmful algal bloom. Hundreds of thousands of people didn't have water for a week or so. This is a big deal in New York State, and it's one of the things that motivates us to take our technology other places, and that's what we're doing. In the next slide, you'll see we were invited in 2018 to help out in Skaneateles Lake. Skaneateles Lake is really similar to Lake George. It's very clear, beautifully clear, like you can see 25 or 30 feet down. Had never had a major harmful algal bloom, and in 2017, late in the summer, they had a big one, and you can see pictures of it here in slide, I think it's 33, and major problems. So we went out there to Skaneateles, brought our technology, again, advanced technology like nothing else people have in the world, brought it out there. And, the first work we did, this is just a freeze frame of a model. This is on 34. And what you're looking at is a cross-section of Skaneateles Lake. This is the modeling team's work from the Jefferson Project. And what I'm going to do, or if you don't see it, you can do it on your end. We're going to, see, can I do this? Oh, I can't do this. There's an animation. In any case, you see on the right-hand side, the bottom of this picture of the lake, this cross-section, is the bottom of the lake. The blue at the very top is the top of the lake. And you notice in the middle, there's this bluish layer. And you see on the right-hand side, it's really dipped down. We call this an internal wave or a Seiche wave. This internal wave goes back and forth. You don't see it on the surface. It's being driven by days of sustained wind, and it's basically making this lake rock back and forth. And what we've discovered when it rocks back and forth, it is scouring the sediments, throwing soil up into the water column, mixing that water, and it looks like that is a great predictive driver of each time they have a harmful algal bloom. So we were able to come in and for the first time give a predictive model of when that lake will have a harmful algal bloom. No one else had ever been able to do that, and that was really well received, and that was part of our work out in Skaneateles Lake. Going to the next slide, we started in Chautauqua Lake this year. Chautauqua Lake, if you don't know, is far western New York by Jamestown. Chautauqua Lake really is the worst of the governor's 12. If you look at that Google image of Chautauqua Lake, it should strike you that the upper part of the lake is pretty clear water, and the lower part is really pea soup green water. To the right of that map, you see a close-up of that water. It is really green. That is a harmful algal bloom happening. You can see it in all these pictures, a real dark green cast to the water. Because of COVID, we're hoping to get out there earlier this year. We actually got out there in late August, and we just pulled our sensor platforms that you see, the vertical profiles. We just pulled them last week out of that lake. And we expect to go back there and help some more in understanding what drives this. And when you understand what drives it, what can be done to mitigate that. So we're working with lots of public and private stakeholders on that. And then finally, that brings us to a few weeks ago. And as many of you know, if you're around the area or you sort of pay attention to what's happening around our area, I told you Lake George had never had a recorded harmful algal bloom. And on early November, they had the first one. This is the place you would say is the last place you expect a harmful algal bloom. The reason is this lake doesn't have very many nutrients. It's hard to feed algae to bloom in massive amounts when you don't have many nutrients. That's why Lake George is incredibly clear. It doesn't have many nutrients, but Skaneateles didn't either. And we now have an idea of how theirs happened. So when that bloom happened, and this is on November 9th, the first confirmed bloom happened, within hours, we had a team of more than 20 researchers working on what happened, how it happened, and how we can understand this. Within about 5 days, we had our initial assessment of what may be happening. We had a team out there measuring all of the physical things we mentioned with those sensors, so the temperature from the surface down to the bottom, the oxygen, the chlorophyll. We had teams, as you see one of our teams out there, sampling the water, sampling the algae, collecting water to test the nutrients. We've done remote sensing work. We're now running the models on those areas, and I should point out in this map on the left, these are the 4 areas where algal blooms were seen, these aggregations of floating algae, and those are the places it was seen. So right now we're trying to understand, and we have a good amount of data to help us. Was this an unusual but natural event, or was this an event that had some influence of human activities? We have a lot of work to do on this. We have a massive amount of data, and one of the things we're so fortunate is that the Darrin Fresh Water Institute has monitored this lake for 40 years, and the Jefferson Project has had advanced sensors for the last 6 or 7 years. We have a tremendous amount of historical data, so we can ask, have we ever seen nutrients at this level in November before? Have we ever seen this algae, this cyanobacteria, at this level before? And we know some of those answers. One is we know what species was causing the bloom. We know this species is pretty common in the fall in Lake George. It's probably been in Lake George for eons. It was apparently coming to the surface in lots of different places around Lake George, not just in those areas I've indicated with red. So we have a lot to go on. It's going to take us a few months to figure it all out, but we're going to do it very carefully, and we have so many different ways from the modeling data. For example, I said we had circulation models. Right now we're running those models and validating them to ask, is it in fact the case that there was surface water circulating into those bays and carrying algae from the main lake, in which case, excuse me, one hypothesis is that this algae lived throughout maybe 30 feet of water, and if you can see my hands, under really calm conditions on November 8th, 9th, it surfaced and sort of collected at the surface, which algae do under very calm conditions, and then got moved into these bays. That's one hypothesis. The other is that it was locally growing in these bays and accumulated for that reason. So we have all the data we need to differentiate between those. It's going to take us a while to get all of the lab water analyzed, the algae analyzed, et cetera. But the good news is we are in such a great position because of the history of the Darrin Fresh Water Institute and the history of the Jefferson Project. We are going to figure this out, and we're probably going to figure this out in a matter of a few months, which is really fast given all that we have to do to figure this out. And we'll work with the New York DEC and the Lake George Association and others to help figure this out. So good news on that front. Bad news that it happened. Good news is that we're in a great position to help understand it. And the last thing we want to talk about is we want to think about solutions. We work, of course, with the Fund for Lake George. And the Fund for Lake George and lots and lots of partners around, the government partners, private NGOs, et cetera, all working together to partner, to innovate, to have investment, and this is their whole strategy of how to actually make a difference. Their big areas are invasive species, try to keep them out, salt reduction, because salt in Lake George has tripled over the last 40 years, bring in this advanced technology with the Jefferson Project, and really focus on water quality and clarity by helping improve septic systems, wastewater treatment, stormwater treatment, et cetera. So they're on all of those fronts making great progress. This is just one example, bringing together all of the interested stakeholders about can we smartly reduce road salt? How do we reduce road salt without compromising driver safety? It turns out we can do it. We are doing it, and the community now has reduced road salt by about 30% in a couple of years, which is remarkable. Think about any other environmental problem to reduce by 30%. Their target is to reduce it by 50%. Again, doing it in an intelligent way with new technologies and not compromising road safety. So lots of details in that story that I don't have time for, but I'm happy to take questions on how they're doing it. The other thing that's really fun is we've we've worked with lots of different departments, lots of different centers, and we work with the group over in Haas and Kathleen Reese and her team working in games and art, and they have put together, I have the website here if you want to see it. You know, a still image doesn't do it justice, but when you have a chance, if you would, look at that website and you will see what they have done is made games that animate the microscopic organisms, the plankton that live in Lake George. And it's such a fun game. They've now got it up at the Leahy Eco Center on Lake Champlain, where about 160,000 visitors come and see this game and play this game. And it really brings people in because these microscopic creatures are so interesting, and people largely have never seen them. They don't even look real. They look kind of alien. But the folks, it was a huge hit. We had a temporary exhibit for 4 months, and they've asked us to come back as a permanent exhibit at that place. So we have 160,000 people every year learning about Rensselaer, learning about Darrin Fresh Water, learning about the Jefferson Project, and getting educated about why they might want to care about water quality. On 42, we have another effort of ours, which is up at the Adirondack Experience. The original name was the Museum of Blue Mountain Lake. And we also have a display there to educate people about the importance of protecting fresh water. That is visited by, I think, about 80,000 people a year as well. So really trying to get the science out to the public and engaging with lots of different people from RPI to make that effort happen. On 43, you'll see that the approach that we're taking really is novel. We're getting lots of great press about the work that we do, the technology that we do, the biological discoveries that we've made. And it's been really well received as really the way to do lake research and to help protect fresh water. And 44, you'll see this is really, I think, a tremendous example of what President Jackson calls the new polytechnic. It's all about bringing in a large diversity of people from all different areas. As I mentioned here, 26 faculty at last count, 12 departments and centers. There's people from the School of Architecture, from Haas, from School of Science, all kinds of departments, multiple engineering departments. And that makes it really effective. It makes it really fun to bring in this diversity of people with all kinds of different viewpoints. And that's been a real pleasure, bringing that many people who really want to contribute to a very important human issue. What we're trying to do, as you can see, is build the future of freshwater protection, starting at Lake George, expanding to other places in New York, expanding to other places around the world, to bring the technology to these places and help them protect their really valuable freshwater resources. And here we are at the final slide, and I want to thank you so much for your attention, for spending your evening with us, and I'd be delighted to take any questions you might have.
Thanks, Dr. Relyea. We have a couple that came in before today's event, and then I have a couple from the group. We'll start with Chris McKenna from the class of '93. As the queen of American lakes, it's provided a strong balance of nature in the watershed environment. You spoke to the algae bloom as, how the Darrin Fresh Water Institute and the Jefferson Project has benefited from the monitoring, but can you also speak to some other introduction of technology into the lake that's affecting that balance as well?
Yeah, so the technology and the experiments and the modeling, all of those together have helped us in a number of ways, not only in harmful algal blooms. One of our great examples is understanding what's happening in road salt pollution. Road salt is one of those things that people don't think about very much. Certainly, scientists didn't give it much thought until maybe 5 years ago. A few did, but not much. And it's striking because we drive on it, we walk on it, we see it everywhere, but not much had been done in terms of what the impacts are. Through the monitoring that we do, through the experimenting that we do, we know an awful lot about what road salt does now, and that helps us think about why we ought to fix it and how we ought to fix it. For example, just the stream stations tell us that you might understandably think road salt is a problem in the spring when snow melts and it runs into the streams. It turns out that you continually have high amounts of salt coming in those streams, even in the late summer, early fall. All of that came from winter applications, but it's sitting in the soil, it's sitting in the stream beds, and it continues to come out of the soil and out of the stream beds way into the summer and fall. We've learned that road salt can do really surprising things. For example, it can change the sex of frogs when they're living in salty environments as tadpoles. It can get rid of the circadian rhythms of some of our plankton, which is the same circadian rhythm you and I have. They flatline. They don't know, when it's morning, when it's night, and that's really important to the ecology of the lake and water quality. We understand that when we first arrived, people were asking the question, which road salt should we use? Should we switch to, the most common one is sodium chloride. Should we switch to magnesium chloride, calcium chloride? Because those are reported to be safer. And it turns out we actually didn't know if they're safer. So we did a lot of experiments and we found out they were not safer. All of that helped motivate the idea that the solution isn't a different salt. The solution is less salt. And that has made a major difference driving a lot of those changes I've talked about.
There's two similar questions to, the technology that we've been able to bring to Lake George, and whether or not, using that, are we able to identify some findings that you presented, like what's the annual water turnover for Lake George, outflow versus inflow, and, why is the algae so high in the Narrows?
Yeah, great questions. The turnover of the lake is approximately 6 to 7 years. That is, when a molecule of water comes in somewhere in the lake, it takes about 6 to 7 years to go out to have a full change of that. The algae, I guess it depends on whether you mean the algae in the water that's floating or the algae that's attached down to the bottom. One of the things that we've done, we worked with a lot of landowners to measure the amount of algae growing all along the shorelines. The Narrows is one of the toughest places because there aren't really very many homes in the Narrows. But as I shared on one of the early maps, we are working to figure out where are the hot spots for algae, because that also typically translates, those are hot spots for nutrients. And then you ask why? Why are those hot spots? Are there nutrients leaking in that shouldn't be, or is it natural? And we can figure that out.
You showed us the live dashboards, Dr. Relyea. We have a question of, whether or not that history that you have there over the last 40 years of the project supports conclusions on things like impact of human activity and climate change.
Well, I'd say, we just published a paper in the past year, and that paper looks at the first 37 of those 40 years. There's no question, because you can look at the data and it's available publicly. You can see the data for yourself that Lake George over 40 years has increased in temperature by about 2 degrees Celsius. That is really similar to lakes around the region, lakes around this latitude of the United States. Most of them are changing by about 2 degrees Celsius, so it's slow, but it's 2 degrees. While that might sound like much, that can have a big impact on when the ice comes. Does the lake ice over or not? We have far less often seeing ice over of Lake George than we did 50 years ago or 100 years ago. That's also a common observation for lakes around New York State. The ice melts earlier by maybe weeks in lakes like Lake George. So yeah, there's a lot of impacts that we can see, and just one of them is the temperature of the lake, which really represents the impacts of the temperature of the air.
Michelle Norton, class of 78, and parent to another alum from the great class of 2011. They consider themselves as citizen scientists, so they want to know that raw data and measurement that you're publishing, is that available for people like them to play with?
Absolutely. So, if you go to the Jefferson Project website, which you see listed right there on your screen, on the final slide, you can find our research papers, and our research papers also direct you right to the original data that we use to make those conclusions. You're welcome to look at that. You can download it. It's publicly available. The sensor data and modeling data, that's in the neighborhood of 120 terabytes, which is far more than anyone can probably handle anyway. But we're working on making more of that available in the future. But if you just want to see some really nice data about the how the lake has changed over 37 years, that's publicly available already.
Great. Ira Goldman from the classes of 1968 and 1969 is on Cayuga Lake, but he's been working with New York State and the HAB initiative with the Seneca Lake Association.
Yeah.
And they want to know the smart data collection buoys that are currently on Seneca Lake, was that developed as part of the Jefferson Project and the research we're doing with New York State?
I believe on Seneca Lake, those are U.S. Geological Survey buoys. They're somewhat different. They are the kind of buoys you can get that are commercially available. I don't know all the details of that, but I know some others that they put out there. Really nice systems, different from ours, but really nice systems to track what's going on in Seneca Lake. And again, you know, the more data, the better. The more people out there measuring things, the better. They do some things that we don't do, and vice versa. And some of that data is also available on the USGS website that I'm sure the folks at the Seneca Lake, their lake association, will probably be able to point you right to where those data are made available on the website.
A lot of questions on the algal blooms, Dr. Relyea. You know, you provided a couple of updates from the last couple of weeks, but you know, any additional information on, you know, what the impact could be, you know, in the next year or two, based on what you've observed in November?
You know, it's a fantastic question, and it's one that we all want to know. Is this an unusual, rare event, and will it happen again? You know, typically harmful algal blooms happen in July, August, September, when things are really hot. There's a species that is really common called microcystis. That's not what we're talking about here. We're talking about a very different organism that's common in the fall. In many lakes where they have these big microcystis summertime blooms, when it happens the first time, you're more likely to have it the second time. I would say we can't make that conclusion yet in this case. We just don't know. There's a whole lot of work that we're doing to find out, for example, how rare was this unusual weather? How rare was the abundance of this particular species compared to previous years? So I would say the jury's still out on that, but we hope to have insights on that in the coming months. And you know, we fully appreciate everyone really wants answers now, but we also want to be very careful that we do it well and we do it right to get the right answer, rather than a quick guess that turns out to be wrong. So it's a lot of different kinds of data still being processed right now, but we will follow up on that and give our best estimate of what the causes were. And understanding the causes also gives you some understanding of that question, of the answer to that question, which is what's the likelihood it would happen again.
I think there might be a few people that are concerned on the likelihood, because there's a question, Dr. Relyea, of how many people use Lake George for drinking water.
A lot of cottages for a long time take their water out. Some treat it, some don't. The Department of Health in New York encourages everyone to treat their water, not just for this, but for all sorts of potential pathogens that could show up, you know, ephemerally. You know, that you might have been good for 10 years, but it's really a good idea to have some filtration on your water just to, so that doesn't happen. You know, the risk is probably lower in Lake George than some other lakes, but it's just a really good idea, which is why the Department of Health puts out that guideline. But lakes like this, you have either the public water systems are taking water from that, you know, Skaneateles, 120,000 people, I think, in the city of Syracuse use that for drinking water. And in Lake George, an awful lot of cottages use it as well. So certainly I encourage anyone who doesn't filter their water. It's a good idea, even if it hasn't caused problems. It's probably something worth thinking about.
Great, thank you. And one of the questions earlier, it seemed, from Laura Warner from the class of 92, just wanted to mention that her summer session at the Darrin Fresh Water Institute was one of her happier experiences at RPI. So thank you, Laura. And she's so glad to hear about all the great research still ongoing.
Thank you for sharing that. And I'm delighted because I hear that a lot. You know, we still have the this first year program where the first year students come in and spend time with us. We have students from the Harlem Academy come up in the summer. We have so many sort of K-12 groups and college groups that come up. We're delighted to do that. I think our annual outreach is about 1,000 person days, which means we're helping 1,000 people every year learn about Lake George, learn about Darrin Fresh Water, learn about Rensselaer. It's really one of our favorite things that we get to do.
Thanks. I know we're approaching the bottom of the hour. Dr. Relyea, for anyone that wants to get more information on importing some of the technology or information to maybe lakes outside of the current initiatives that the Jefferson Project and Rensselaer have, would that be something they could go to the website about or reach out elsewhere?
Yep, the website is a tremendous source of information about what we do, how we do it, publications that we've done, presentations that we've given, news that comes out. So the latest news, we have a new web page as part of that website on the Lake George Harmful Algal Bloom and what our response to it was. So there's a wealth of information there. As I mentioned before, you can go to jeffersonproject.live and look at the sensors putting out data right now. And you can look there 365 days of the year and see the different weather. So lots and lots of information to look at there and enjoy what you can learn about.
Thanks, Dr. Relyea, and thanks for speaking to this topic tonight with this group that attended.
Oh, thank you for the invitation, and thanks to all of you who joined. I appreciate you taking time out of your busy schedules and especially out of your evening. So thank you for attending and letting me talk about it.
Right. So it's our hope that tonight's event gave an insight into how even under the present circumstances facing our globe, Rensselaer continues to advance the studying of our fresh water with a goal of understanding the impact of human activity on it and how to mitigate those effects. Before I pass the closing of the evening's event back to the alumni relations staff, I want to wish all of you, thank you. Continue to stay safe and be well, and best wishes for a happy holiday and healthy new year.
Thank you, Michael, and thank you, Dr. Relyea, and to all of our guests for joining us this evening. Today's event was recorded, and we will share it with you as well as the links that Dr. Relyea shared throughout the evening. This event, alongside of many other virtual events and alumni chapter events that have been hosted over the last 8 months, are hosted on our website, and we will include that link for you all in the email follow-up. We would also like to invite you to our upcoming events, including on December 10th, a discussion co-sponsored by the RAA chapters of Boston and New York City in partnership with Rensselaer's Center for Supply Networks and Analytics, titled A New Kind of Holiday Season, COVID's Impact on the Supply Chain and Consumers. I'm sure we're quite interested in that. And on December 15th, a virtual global game changer panel, online, the influence of biotechnology in a changing world, sponsored by Rensselaer and the New York City Executive Council. And finally, now more than ever, your support is needed to continue the exceptional tradition of a Rensselaer education for our students. Please visit our site to learn more about other ways you can support our students throughout the annual fund programming at giving.rpi.edu. And just as Michael shared, thank you for joining us today. Stay safe and healthy, and have a great evening.